Okay, so we would like to talk about the prime number theorem. So the prime number theorem is maybe one of the most celebrated theorems of mathematics that allows us to draw some conclusions regarding the probability that a natural number in a given range is prime. In particular, the way that the initial conjecture was made before this was a theorem, one wanted to have an estimate on how many prime numbers less than a given number exist. So, in other words, what is the amount of primes that do not exceed the number x? Classically speaking, this is something that is denoted by pi of x. So for example, there are 4 prime numbers that do not exceed 10, or there are 25 prime numbers that do not exceed 100, and so on and so forth. So one would really like to compare the amount of such numbers with how many numbers we consider. So in 10 numbers, so that tells you that the amount of primes in the first or the percentage of primes in the first 10 numbers is 40%. Then in the first 100 numbers, it becomes 25%, so it drops. And in general, we would like to know what proportion of the first x numbers is prime. So by looking at different tables, Gauss was able to conjecture at a very young age that pi of x is approximately equal to the integral from 2 to infinity of dt over log t. Again, log here is the natural logarithm, the only logarithm we use in mathematics. This is, oops, sorry, not to infinity. That would be a problem. I meant to say to x. Okay, after all, I have to give an expression. This is called the function lie, so that's lie of x. And actually, if one uses L'Hopital's rule, you can show that this statement is also equivalent to pi of x be given by x over log x. So this somehow tells you that the proportion of numbers among the first x numbers which are prime is 1 over log x, or this can be considered as the probability of the first among the first x numbers to have a prime number, and that probability tends to 0. So that was conjectured by Gauss, but it took almost 100 years, so this became a theorem in 1896, proven by Hadamard and de la Vallée-Poussin. So we can state this in a more rigorous way by saying that the limit of pi of x, again, pi of x from now on, and we will encounter it again, is this amount of prime numbers that do not exceed x over x over log x is equal to 1. Prime number theorem has a very, very interesting story. So for several decades, there was no real progress. And then there were 2 mathematicians who really paved the path pointing to the proof, even though they did not give the proof themselves. The 2 mathematicians are Chebyshev and Riemann. And you may argue that, one might argue that in some sense, they built all the infrastructure that was needed. It was anything but a trivial task to actually take the last step. So the 2 mathematicians that proved it did some phenomenal work. And once this theorem was known, people wanted to give different proofs and understand it from all sorts of different perspectives. One might argue that, first of all, the initial proof was very much dependent upon complex analysis. That made some people a little uncomfortable. People looked for proofs that did not involve complex analysis. The first two such proofs were given by one joint proof by Erdos and Selberg. That's actually a very interesting story of why one should call it a joint proof, and then there was an independent proof by Selberg. That's a very, very interesting story. One should say a few things about it. Eventually, there have been many, many different proofs of the prime number theorem, and the most beautiful proof, one might argue, is a proof given by Donald Newman. This proof does not avoid complex numbers, but it uses them in pretty much one step, one final step, and it involves a variation, if you like, of the zeta function. It's a very remarkable proof. It's short, and it's based on an amazing remark that Donald Newman made in order to translate the prime number theorem into the convergence of an improper integral. Hopefully we'll come back to this and discuss this proof, but for the moment being, we will leave it at that. And on a separate video, we will try to give Chebyshev's functions. Thanks for watching.